Detection of FM waves. How we are going to detect the modulated signal that we are going to receive in the receiver section. So for that, we have to define methods, direct methods, indirect methods. In the direct method, most popular is the balanced frequency discriminator. In indirect method, we have phase lock loop, that is also called as the PLL, and zero crossing detectors. So here you see that how we are going to detect the signals, and PLL is going to be more important. Apart from this, we have balanced frequency discriminators. We have slope circuits. With the help of slope circuit, we'll try to obtain in case of balanced frequency discriminator. In case of PLL, you'll see that how voltage control oscillator is going to play the role. So still you didn't subscribe our channel, please subscribe it and share with your friend. So first method is here, balance frequency. Name is what here? Frequency discriminators. Okay. And balance. So balance means we are going to use something, two things that is going to balance. So here later we'll have two slope circuit. Okay. So we'll see that slope circuit 1 and slope circuit 2, how it is going to balance here to obtain this modulated wave. So it is the direct method, okay, for demodulation of FM signal here. So we have to obtain the here instantaneous output amplitude is directly proportional to the instantaneous frequency of the input FM signal. Okay, this is the main basic logic on which you are going to work. Now we have the basic component of this one is the slope circuit. So later we'll see with the help of diagram like here how this slope circuit is going to play the role. Okay. So that diagram you want, you can draw this one in the starting also. So here what we have, FM wave, that is the modulated wave. Then we have slope circuit 1 with function h1 of f, slope circuit 2 with function h2 of f. Then we have envelope detector for both slope circuits. And finally, it is given to the summer. One is given with plus sign, another with minus. So finally, we are able to obtain the baseband signal here. So that's why we are talking here about the slope circuit, okay, and the transfer function. So it has slope circuit followed by the envelope detectors, and finally that is given to summer. So now we'll discuss separately what is the ideal slope circuit and what is their frequency response. So its response is purely imaginary and changing linearly. So finally we are going to define the for the slope circuit 1, that transfer function is h1 of f. So that is given as j2 pi a of that is into f minus fc plus bt by 2. So beta is the transmission bandwidth. So in the range of frequency fc minus bt by 2 to fc plus bt by 2. Similarly, here we have j2 pi f plus fc minus bt by 2. You see that here this portion is going to change. Okay. Here we have done f minus this one. And in this situation, in second one, we have f minus this. Okay. So finally, f minus minus will become plus fc, and this plus bt by 2 become the minus bt by 2. So this is the range of the frequency, and remaining other place it is 0, where A is the constant. So finally this one, if you want to see in terms of that is the spectrum. So here we have slope is the 2 pi. Here also slope is going to be the 2 pi. Okay. So this is in the range of fc minus bt by 2, fc plus bt by 2. Okay. And again, this one is the minus fc minus bt by 2. So in this range, okay, here we have response for this. After that, in entire, it is going to be 0. Again, here we have response, and this is the vertical line. So like this, how we are going to draw this equation 1 in terms of diagram. So this also can be explained, okay, by the help of real values, and it is going to pass through the band pass filters, and then we are going to obtain the corresponding complex value through the low pass filters. Okay. So now we can replace these band pass filters with frequency response h1 of f with an equivalent low pass filter that is going to produce the frequency response of h1 of f bar or approximate. Okay. So here we have earlier band pass filters, again low pass filters. So better we are trying to obtain by the help of single filter. So that filters should generate, that low pass filter should generate the frequency response as H1 of F approximate. So how can obtain this? If you are going to shift H1 bar of F to the right side by the FC, and we are going to set like this, H1 F minus FC bar is going to be 2 times of H1 of F for the positive frequency. So that these two conditions we have to take care when we are designing the low pass filter. So in that situation, we should get H1 of F minus Fc of bar equal to 2H1 of F for the positive frequency. So now we are going to utilize that equation 1 as well as equation 2. And we are sitting here, okay, right side, okay. So that you know that if any function have f minus fc, that is going to shift right side, f plus fc is going to shift the left side. So we have 2 times of this. So 2 is already there. So 2 into j2 pi, here fc plus bt by 2, okay. And here this range minus bt by 2, 2 plus bt by 2. So finally, that response of low pass is going to be in this range. Now slope become the 4 pi a, and range of the frequency is minus bt by plus bt by 2. So here this bt is the transmission bandwidth. Now we are going to consider the general modulated wave what we are going to obtain, that is AC cos 2 pi ct plus 2 pi kf integral of m of tau into d tau over g to 0 to t. So this expression already aware, already available in the previous lecture also when we're talking about frequency modulation. So here what is the consideration that this carrier's frequency should be greater than the transmission bandwidth. And transmission bandwidth we have seen that is the 2 into del f plus 2fm. So here 2 del f we can take common. So we have expression, okay, here we'll get fm by, if you have 2 del f you have taken common, okay. So the fm by del f. And you know that this also can be written as 1 upon del f by fm. And del f by fm is what? Beta. That's why it's written as 1 by beta. Del f is the frequency deviation, fm is the frequency of the message signal. So this complex envelope of this S of t can be given as S cap of t or S approximate of t AC exponential j2 pi kf integral over 0 to t of m of tau into d tau. So since e to the power I theta is what? Cos theta plus sin theta. So that things we are going to see. And this message signal is where? In the second term only. So that's why it is written in this portion. Now this S1 cap of t is the complex envelope of equation 1. So this can be expressed by the help of Fourier transform. So now this time domain is being represented in the frequency domain. That is 1 by 2 h1 of f cap into s cap of f. So this formula you need to remember how we are going to have. So now we substitute the value of h1f already we have. So that 4j4 pi a. So this 2 is there, due to this is going to get cancelled. F plus bt by 2, and here we have taken s of f bar as it is. Okay, in this range it is defined, otherwise it is going to be 0. This is now our equation number 6. So this equation number 6 also can be written in the time domain when we're talking a into a is the constant taken outside. It is the differential of s cap of t plus j pi beta t s of t cap. So now here in this we can substitute the value of s cap of t that we have in the equation 5. So then we are able to obtain the equation 8. How we are getting the equation 8? So for that here it is given how we are going to differentiate all these things. The steps are given here. So here first exponential e to the power I theta. Okay. So that e to the power I theta, if you have, if like we have e to the power ax. So what is the differentiation? In the same way, here we are going to differentiate exponential of this with the respect of this entire term. After that, we are going to differentiate again this part. Okay, so that is going to be here 2 j2 pi cap. Differentiation of this integral of m of tau into d tau is the m of t. And the second term, okay, that is just we are multiplying. So we have taken the common and we have equation number 8 that you can see. Then we have desired response of the slope circuit is finally, now we can write that is S1 of t in time domain in the real part of S1 of t cap exponential j2 pi r ct. So now here if you see that we are substituting the value what we have obtained here, okay, this equation, okay, equation number 8. So this will substitute and multiplying with exponential j 2 pi r ct. So e to the power, if you have same exponential like e to the power x into e to the power y, it can be written as e to the power x plus y. So similar operation is written here in this part, okay. And now we are trying to obtain the real part. So again, e to the power I theta is the cos theta plus sine theta. So that's why we have this is the as the real part we are able to obtain. So here already what we have j, okay, and here again we have j that we want we can take common. So finally this part we are able to obtain, and here we have phase shift of pi by 2. So this S1 of t is the hybrid modulated signal in which amplitude and frequency of the carrier wave vary with the message signals. So this term 2 kf into m of t by bt is less than 1 for all time. Okay? So always it is going to be less than. So this envelope detector is used to recover this amplitude variations. Already know whenever, like in case of amplitude modulation, also we have for the detection, we are going to use the envelope detectors. So whenever we have to talk about amplitude, we are having envelope detectors. So that modulus is given as 5 beta t A into AC 1 plus 2 kf by bt m of t. This is the equation number 10. So this here, what you are saying that this term is proportional to the slope A. So and A is what here constants. So it can be removed by subtraction with the complementary slope circuit. So that's why that second slope circuit is what? It is the complementary of the first slope circuits. So that relation of the response of the second slope circuit can be given as H2 of F cap equal to H1 of minus F cap. So that is equation number 11. So similarly, on the basis of this, we can obtain the response of this slope circuit too. So that is going to be this part. So here a small change, you'll see that sign is going to change. So now finally we have difference of both. So that is going to be 4 pi kf A into AC into m of t. This is the equation number 13. So now this again can be represented here with the help. This is the response of this slope circuit 2, and previous one what we have seen, that is the response of this slope circuit 1. So that's why it is the complementary circuits. You will see that both was how turning there in case of previous one what we have in place of this situation is going to be in the way like this. Okay. So this is going to be the complementary of each other, and right side how is the situation? This is the slope, and here we have vertical line. So that's why these both are called as the complementary of each other. Okay. This is how frequency discriminator is going to work to detect the FM modulated signal. Now we have phase locked loops. Phase locked loop is very, very important questions. Okay, so they're asking, explain, anyone they're going to ask either frequency discrimination or PLL, but PLL is very important. You can see this experiment in the lab also. So this is the indirect method for the demodulation of the FM signals. So that was the direct. Here we have indirect method, and another indirect method is the zero detection technique also. So it has three major components. Sometimes they're asking you one last question, what are the major components of the PLL, so that is the multiplier, loop filter, and VCO. VCO is the voltage control oscillators. So that is going to play the big role here. So it is used to generate the any oscillator, you know that it is going to generate the signal. So here also it's going to generate the sinusoidal signal, and frequency is determined by the applied voltage from an external source. So that is a part here. So now we are going to consider that in initial condition, VCO is adjusted, and when control voltage zero, initial control condition means voltage, initial voltage is zero. So now two different conditions is being satisfied. The frequency of the VCO is set at FC, that is the carrier frequency, and VCO output has 90-degree phase shift with respect to unmodulated carrier wave. Okay. So frequency should be FC and phase shift should be how much? 90-degree with respect to unmodulated carrier wave. And this is the diagram of the PLL. Okay, so what you are seeing that your modulated wave is given as the input. Then you have this is the mixture part here. Okay, and we have loop filters, and in the feedback we have voltage control oscillators. So this voltage control oscillator is output is taken as R of t, and here one of the input is S of t. So that's going to generate some error E of t that is given to here loop filter, and finally that PLL output is V of t. So that all expression we are going to see here. So this late FM signal, that is what we are going to give. The PLL is in place of cos, it's written as the sine. AC sine 2 pi of ct plus phi 1 of t. So phi 1 of t, if we consider with the standard equation, what is the value? 2 pi kf integral of m of tau into d tau. Okay. And kf is what your frequency sensitivity. So this expression we have seen multiple times. So now this VCO voltage control oscillator output is defined as R of t is what? AV cos. So since it is having phase shift of 90 degree in compared to carrier, so that's why it is the cos 2 pi epsilon phi 2 of t. So phi 2 of t is what here? 2 pi kV. What is change here? kV. And input to the voltage control oscillator is what? The V of t. If you see the diagram here, okay. Okay, V of t is going to be input to the voltage control oscillators. That's why we've written V of tau into d tau. So kV is what here? Frequency sensitivity of voltage control oscillator, that is given in hertz per volt. So KF, KV both are different. Now this adjustment is done like this, that PLL should generate a VCO output, that is R of t, should have everything should be same except the phase difference of 90 degree. Okay. So now we have to recover that estimate of m of t. That is in demodulation what we are going to do. We are trying to recover the estimate of the message signal. So now after multiply, we have two components. So one is coming from the modulated wave, one is given to the here output of the VCO. Both are given to the multiplier. So it is being output here. Okay, Km ACAB sine 4 pi FCT plus phi 1 of t plus phi 2 of t. So here in multiplied again, we are going to use that formula. We have sine A into cos B. Okay, on the basis of that, we are getting this expression. This is high frequency components, and second one is the low frequency components. And what we are seeing that here Km is going to be the multiplier gain. So now after this, output is given to the low filter, low pass filter. So low pass filter is going to allow which frequency? That having low frequency components. So this second one having low frequency components, that is going to be passed through the filters. So that's why here E of t, we are writing as Km into ACAB sine phi E of t. So phi of t is here phase error. So that is defined as phi 1 of t minus phi 2 of t. So already we have seen what is phi 1 of t and phi 2 of t. So finally that output of the loop filter is given by the help of convolutions. So we are much aware about the convolution. So for any things, here we have E of tau into H of t minus tau into d tau, and range is minus infinity to plus infinity. So convolution, okay. So here H of t is the impulse response of that loop filters, and we are going to obtain the relation. Okay. So finally, we get the nonlinear that is the integral differential equation. For this purpose, when you are going to do the convolution of this, so that equation 5. So now this also we can write d phi of t by dt equal to d phi 1 of dt. So this one, okay, equation number 4, we are trying to write in this format. So that's we have convolution is applied here in this portion, okay, for the second term. So that convolution value is substituted here. How we are going to do? So where you see that K naught is the loop gain parameters. So finally, this equation 6, we are trying to realize with the help of diagram. So finally, error function, what we have here, phi e of t is going to be given as phi 1 of t differential minus what we have, phi 2 of t. So this phi 2 of t value in this portion, what are things we have? This is the sine. So that's why sine, some function, it is multiplied by 2 pi k naught. That's why it's given multiplied 2 pi k naught. Then we have h of t, since we are finding the impulse response. Again, this is given to the multiplier. So we have again 1 by 2 pi kv naught. So, okay, that's output is given as the V of t. And here, this impulse, whatever we are going to obtain, this is the product of this. After that, it should be integrated. That's why in the feedback, what we have, integral of beta over 0 to t. So this equation 6 is being realized here by the help of this diagram. So this is the nonlinear model of the PLL. Earlier, we have seen the block diagram of the PLL that consists of the multiplier, low pass filters, or we call it the loop filter, and followed by the VCO in the feedback. Now there is the zero crossing detectors. This is sometimes they're asking. So in some syllabus it is not there, but it is also important for the computation point of view. So what is the beauty of this one? It is a comparator with reference level set is at 0. And if you see that here, this it is going to help to convert the analog signal into the suitable form. So generally we are going to obtain the rectangular form. Okay. And it is not going to use the carrier frequency here in case of demodulation part. So this digital signal can easily be converted from the FM signal. How it is being converted in the FM signal. So for that, we are going to use the op-amp. Op-amp is what here? Operational amplifier. So one input is given to the positive, that is a non-inverting terminal. Another is given to inverting. Already you are aware of the op-amp, okay? One is the plus, one is the minus. Here the output, okay? You have pin number 2, 3, then 4, 7 is for the supply. Op-amp is what here? IC 741. Okay. So here what they're going to use, they have hard limiter. Okay. That hard limiter is going to convert the incoming FM signal into rectangular waveform. And we are going to use the concept of monostable multivibrators. Already you have studied in the lower class. Mono means only one state is stable, so which is triggered by the rising part of this. So it is converted into rectangular part. This is the rising, this is the falling part. So triggering takes place during the rising parts. So this is the positive edge trigger, like you are seeing in case of flip-flop also. And this pulse and duration is tau. So finally, if you see in terms of relation, then we have 1 by fc is much lesser than time period of this, and time period is much lesser than by 1 by omega, where fc is the frequency of the unmodulated carrier, where omega is the bandwidth of the message signal. So we have again relation 1 by t is the time period integral over t minus capital T to the small t z of lambda into d lambda, that is n into a tau by t. So n is the number of zero crossing. How many times is going to cross the zero? And if you see in terms of circuit, so this is modulated wave is given to the hard limiter. The purpose of the hard limiter is what? To convert this modulated wave into the rectangular waveform. After that, we have monostable multivibrator here. That pulse width is the tau, that is the Tc by 2. So Tc is what here? 1 by Fc. So tau is going to become 1 by 2 Fc. So that is important in part of monostable. Then it has one, you know that monostable internal connections. We have transistors. One is the Q and the Q bar that complement output is here. So that is Z of T and Z bar of T is given to the integrator low pass filter. Again, another integrator low pass filter. So one is omega of T is given to the non-inverting end of the op-amp and omega bar of T is given to the inverting end of the op-amp. So this is the differential amplifier. The difference of these two is going to be available at the output of the op-amp, that is the D of T. So here we have three different conditions we are going to see. When there is no modulation, okay, so Y of T will have 50% duty cycle, means this on time and off time both are going to be same. So there what will have omega of T and omega bar of T both are same. So finally differential amplifier output is going to be 0. Now, as frequency increases above the Fc, then omega of t also going to increase, but omega bar of t is going to decrease. So d of t value is positive here, and it's going to increase with frequency Fc. Okay, so this part is condition when this frequency increases above carrier frequency, omega of t is going to increase, which is given to the non-inverting end. Okay, and omega bar of t is going to decrease. Hence why that differential amplifier output is also positive and it's going to increase as carrier frequency is going to increase. So this is the about this carrier frequency where we have used in the modulation. When frequency is going to decrease. So now it is the frequency is below absolute. Earlier what was? Frequency is, this frequency is greater than absolute. Here frequency is less than absolute. Okay. Then d of t is negative. D of t is negative means what's happening? Omega of t is decreasing, omega bar of t is increasing. Okay. Omega of t is going to decrease, omega bar of t is going to increase. So we have negative output here and its amplitude increases with frequency deviation. Okay, below Fc. Frequency deviation is what? Del F. So finally, binary zero crossing FM detectors can have better than 0%, 0.1% linearity and it can operate up to 10 megahertz. So now here in this part, you see that this is the rectangular wave, which is the output of the hard limiter. And finally, here integral, that is integrator output Z of T and here Z bar of T. And here this is the omega of T towards the higher value and here omega bar of T here coming down. Like how it is going to increase and it is how going to decrease. When it is going to decrease, it is going to increase. And duration of this pulse is what? Tc by 2. So this is the output of the monostable multivibrator followed by the integrator. Okay, so this is how we are able to detect the FM signals with the help of direct and indirect methods. Okay, please write your comments, share with your friends. Thank you very much.